Hello everyone, my name is Nye and I work as a geospatial data scientist in SERVIR Mekong program. And today I would like to present mapping forest disturbance using TensorFlow and Google Earth Engine. As all of you know, forest is a very important natural resource for human beings. So maintaining those forests is also vital task. So forest disturbance alert is a very important information to maintain those forests. So these alerts can be created by using machine learning algorithm with training data and many satellite imagery. So today I want to present how we will be creating this disturbance alert using radars, Sentinel-1 imagery. So why we are using radar forest disturbance? So currently for the forest alert data, we have data from University of Maryland GLAD program. However, they use Landsat 8 optical imagery, and these data are not inconsistent during the rainy season in Cambodia. So that is why SERVIR Mekong plan to develop radar-based alert to allow better monitoring during the monsoon rainy season in Cambodia. So here is our study area, Preland Wildlife Sanctuary, and it was designated in 2016, and it has total of 431,000 hectares. And we also include another surrounding 2 sanctuaries near GPL the expanded study domain allows for a large number of training data, and that will have that final model to generalize for regional monitoring. And this GPL and its surrounding area have experienced very high rate of deforestation every year. So we are planning to focus this area as our study. So here is our system overview. So first, we created our training data set in Google Earth Engine. And after that, we create TF record and export in Google Cloud. And after we export in Google Cloud, we use those TF records in our virtual machine to train our deep learning model. And after we got our trained model, we launched those models in Google AI platform in Google Cloud again. And after that, we create inference in Google Earth Engine to get our output results. And for the validation, we use Collect at Online CEO to validate with near-free planet imagery for our SAR alert. And next, before moving to model architecture, I want to introduce a little bit about TensorFlow and Keras. So TensorFlow is an end-to-end open source platform for machine learning, and it has a comprehensive, flexible ecosystem of true library and community resources, and developer can easily build and deploy machine learning power application using TensorFlow and Keras. And Keras is a Python interface for artificial neural network, and it acts as an interface for TensorFlow library. And in Keras, there are many available pre-trained models that we can use as a transfer learning in our network. And here are the example model like Exception, VGG60, VGG19, ResNet, and MobileNet, etc. And later in our architecture, we will be using MobileNet as an encoder in our architecture. So here, as all of you see, MobileNet, the size of MobileNet is very small compared to other models. It only have around 40 to 60 megabytes, and its accuracy is quite comparable to other models. So that is the reason we are using MobileNet in our architecture. And here is our model architecture. So our main model architecture is UNet. So the architecture shape is like U shape, and there are 2 parts in UNet. and encoder and decoder bed. So here, this left side is encoder bed. And for the encoder bed, we use MobileNet v3 as some block from MobileNet v3 as an encoder. And MobileNet v3 is the advanced version of MobileNet v2, and it includes QUID and ASICs as the output after the bottleneck residual block of v2. And the accuracy of v3 is better than the MobileNet v2, and we are using those as an encoder in our architecture. So here we have 128 into 128 size image, and we encode it to 6432 NT8. And after that, we decode these image patches, and at the end we got our original image size 128 into 128 size image. And at the end, we feed through with sigmoid activation function to convert output value into probability distribution or two classes, disturbance and no disturbance, as the output. So for the detailed methodology, first, we perform random data augmentation to generalize our data sets, and we just did augmentation using 0, 90 degree, 80 degree rotation. And we optimize our model with Abdel Optimizer, and we train using batch size of 60 and approach, total approach of 14 for our model. And for the loss function, we use dice lot as a loss function. And for the performance evaluation, for the training and testing, we calculate categorical accuracy and F1 score, recall, and precision. And these the figure in the left show the accuracy of training and testing data sets for both of ascending and descending orbit. And the table here show the model validation result for the ascending and descending model. And for the ascending orbit, the accuracy is 0.92%, and descending orbit, the accuracy of 0.90%. So ascending orbit has a little bit higher accuracy than descending in our model. And for the validation, we perform independence validation. And for this independent validation, we collaborate with US 8-granny prevalent team and other NGO and university team for this validation. And here we use Collect at Online for the past year from 2018 to 2020 with planet imagery. And we create some example or strategy for the validation. And in the right figure, you can see how we can use CEO to validate our imagery. So we use 3 categories and we validate. And this is the result of the validation. So this is independent validation result for 2020. And here, what season consider June to August in the table. So in here, we create stratum as you see in the figure. So glad dry, sour dry, and dry, glad dry, wet, and sour dry, wet September, October, November, and no disturbance with the total of many points. And here we can see we got highest accuracy for both of glad and sour dry season. And for the wet season, we don't have, the accuracy is not good. And this is the system output. So for the output, we will be creating Google Ad Engine app for the user to support for the user. And the alert will be created every 6 days when Sentinel, when overpass and update inside alert system. And this app engine tool can support user to identify default interest, and they can view alert along with GLAD alert and Sentinel to image. And they can export alert by pre-defined protected area, and it's date, and after that they can process further analysis in their designative tool. Thank you everyone for your interest in